I will share my screen. All right, so last week we covered the material until 11.5, the section gradient descent in Bellman error. Yeah, quick recap of what we covered last week. So essentially, in a couple of words, there are a bunch of different ways to represent error corresponding to our approximated value function and the true value function, and all those errors are different, and that is because our function approximation space, so the space representable by a function approximator is restricted, and the true value function might not respect those restrictions. Therefore, it's not always the case that we can do so. The final solution we arrive at using, for example, minimize, so the point in the function approximation space that minimizes the average temporal difference error, or Bellman error, or projected Bellman error. All those can be different points in our function approximation space, and that makes things a bit complicated. But this week we will have a look at some proposed solutions to this problem, and how can we learn a useful value function using function approximation with off-policy data. And first, let's have a look at what might seem like the most evident solution, as a gradient descent in Bellman error. And as you remember, the problems are coming from the fact that we are not using so with algorithm we considered before, we are doing not a true gradient descent, but a semi-gradient descent. And with off-policy, when we combine this with off-policy learning function approximation, and the third, what was the third component of the deadly triad? Yeah, bootstrapping. Okay, so this this results in a potential divergence of the algorithm, and therefore we might want to try to do a true gradient descent. And let's first have a look at what would we get if we will try to derive our objective in a way that it minimizes the TD, the average TD error. And so the previous objective, as you remember, it wasn't like minimizing a gradient of any function exactly. We were kind of ignoring the fact that we are bootstrapping using the same like function approximator determined by the same weight vector as we that we are trying to update, and therefore we are getting like not a true gradient algorithm. So we can find the what would be the gradient update that correspond to minimizing the expected TD error here. Brief recap: the expected TD error would be a sum over all states of the expected square of the of this error here, and weighted by the distribution of states given by this mu. And the distribution of states in this case is derived from the policy we want to evaluate, so the pi target policy. To switch it to evaluate this value under using the data from behavioral policy B, we can use important sampling ratio. So these two are equivalent, but in the first case we have actions from the target policy, and in the second case we have actions from the behavioral policy. So this is what we actually have in our case, like what we can really observe. And that would be, that can be rewritten as just an expectation under behavioral policy of this quantity here, important sampling ratio times the squared error given by this line, by this expression. Okay, which is actually like kind of our, which is difference between the approximated value and our estimate of approximated of this value given the new observation, right? So that is the error we are trying to minimize, temporal difference error again. So we can now get the gradient of this objective and write our update in terms of that gradient. So
sorry, Arto, do you know how you get from the first line of the gradient to the second line? Is that just
the first line and the second line? So we have just we are trying to find here we write it with respect to delta. So we just get, we had 1/2 here, then we have this 2 rho delta, right? It's just a formula of the derivative from calculus.
Right.
And then, so here we take the gradient with, gradient of this function here with respect to delta sub t, and that would be just that function multiplied by the gradient of delta sub t, and then we write that out because actually we need a gradient with respect to w, so then we can kind of expand it. So that would be a chain rule. So the first, from first line to the second line, it's just a regular formula for the derivative of squared like value, right? And and then we apply a chain rule to get to the third line.
Okay, sure.
Yeah, cool. So. Right, so we have this update rule, and that we will call a naive residual gradient algorithm. And this is, so this would be a stochastic gradient descent in this case. We have a complete gradient with respect to the like of our v hat with respect to w, and yeah, so here we still don't have this like explicit formula for the update, because it depends on what would be the our function we had. But in the simplest linear case, that would be just our feature vector, right? Because the gradient of we had, if in the linear case, would be just a feature vector that we multiply with w. Okay, and here there is an example that shows us why this algorithm fails. So the value it converges to is not a value, is not the value that optimizes our. So we do not find the true value function, and so for let's consider this simple example. We have 3 states, and and we have a stochastic transition with equal probabilities from state A, and it produces a 0 reward. We can transition to B and C with equal probability, and then from both B and C we have a deterministic transition with reward 1 from B and reward 0 from C. And all right, so in this case, the true value for A would be 1/2, true value for B would be 1, and true value for C would be 0. So that is kind of, that is obvious from this small MDP. Okay, but however, if we do the calculations, this naive residual gradient algorithm converges to different values. So in this example, they show that B will have 3/4 and C will have 1/4 value, and A will be correct, 1/2, but the other 2 values would be wrong. So, and why this happens? Because what we are minimizing is this expected temporal difference error, but it is not like we do not, as it was shown in that how it's called, error function geometry section, the TD error. So the point that minimizes expected TD error is not the same as the point that minimizes, for example, Bellman error. So which would be where our so we have like approximate value function, and where it is closest to the true value function. So yeah, so they write it down, and they show that indeed the TD error will be minimized by this solution, with 3/4 for B and 1/4 for C, while and if we set the B and C to be the correct, like true values for this MDP, the TD error will indeed increase. So that, and yeah, so that example demonstrates that there is a problem with optimizing for this TD error directly. So that's not the best objective. Yeah, but so this algorithm will robustly converge. So it has all the convergence properties of the stochastic gradient descent, but the point to which it converges, it is not the point we are interested in. at least not always the same point as we want to find. Okay, so now let's think what would happen if we do another most intuitive thing. So we can design our objective to minimize the Bellman error, the expected Bellman error. And again, we can get update rule that would correspond to the Bellman error. So here we go through the process of deriving it again. We start with the expectation under our target policy, then we switch to using importance sampling, we switch to estimating and using behavioral policy. Then we write down the gradient again, and in this case we have this we have these two expectations, and we have this like the same problem, which is so we here we have these two expectations, and the samples are not independent. So we kind of to optimize this directly. So we need to sample here. So to apply the stochastic gradient descent, we need to sample, and then like after many steps, if we decrease learning rate appropriately, we will converge to the local minima or global minima in case of convex functions. But to make this work properly, we need two independent samples for state t plus s sub t plus 1 and s sub t. And in many cases, we cannot get these samples. Well, basically, when we have this data generated by the real world interactions, we never can get the samples independent samples for s sub t and s sub t plus 1, right? Because our s sub t is always kind of followed by s sub t plus 1. We have only one kind of sample for each trajectory. And this can be resolved by in some cases. For example, this is not an issue when we have a deterministic environment, and because in that case, like the sample will be always the same. Therefore, we don't need to worry about having this value sampled independently. And another way we can do it, so we can, if we are running the simulation, we can draw multiple samples from the same state, and then we can use independent samples for s sub t and s sub t plus 1. But there is yet another kind of deeper problem related to that. And yeah, so let's first consider this modified pre-split counterexample for the Bellman error. And in this case, we have like two states, A sub 1 and A sub 2. So you can see that in this case, the MDP is deterministic, but we are approximating the value for A1 and A2 with the same, I think, with one parameter. And in this case, the algorithm will again converge to this RON values here. So when you observe the samples from running this MDP, or that we can call it probably Markov reward process, because we don't have much choices here. The data will be identical to that generated by the previous example, this one. And essentially, they drive us to this problem that Bellman error is not learnable. And what learnable in this case mean that it cannot be identified. So we cannot identify unique value for Bellman error from the data. So here is another example which demonstrates this failure case when we cannot learn a Bellman error. So we have two MDPs or MRPs, one with one state, and we have transitions like this transition from this state back to itself. And with equal probability, we get a reward 2 or reward 0. And another case when we have two states, and we get reward 2 from one state and reward 0 from another state. And the data, the trajectories generated by running simulation for both of these MRPs would be identical. It would be a sequence of interleaved zeros and twos. And we cannot uniquely identify, so we cannot distinguish between this MRP and this MRP by just observing the sequence of rewards. So in this case, but the value error, the expected value error corresponding to these two MRPs is different. So here you can see that in both cases, the value of the state, so here the value of one state is approximated by the weight W, and here the value of both two states is approximated with the same coefficient W. And so true value in this case would be 0 for the left state, this one, and 2 for this one, because all the rewards following this state are 0 and 2 respectively. And the true value for this state is 1, because we have the transitions with reward 0 and 2 with equal probabilities, right? And so the value error when we in both cases we can set W to 1. That would minimize the value error, but value error in these two cases will be different. It will be 0 for the first case, and like 1 plus 1, and like, so it will be non-zero for the second case, right? And so the problem is we cannot uniquely identify the value error from the data only if we don't know nothing about underlying process here. So yeah, I think the best illustration here is showing this problem can be seen here. So we have a data distribution, and we have two Markov decision processes that generate the same data distribution. And there are two unique different value errors that will correspond to this MDP and so here W star is optimal weights for that MDP when using that particular function approximation as shown in the example, right? And so here for the Monte Carlo objective, we use the true returns from the Markov reward process to learn the weight in W. And although the value error is not learnable, we still can learn the optimal W in this case, because so optimal W would be the same for both scenarios. So that's kind of interesting. But now let's look at the bootstrapping case. So again, both MDPs have different corresponding expected Bellman error. And when minimizing for this Bellman error objective, so we will get different W's that minimize the Bellman error for two cases. And that is a problem, because this means we cannot learn an optimal W from Bellman using Bellman error, right? Because these two are indistinguishable from data, and we are learning from data. But the values for W optimal values for W are different, but data is the same. So we cannot find this solution from the data. We need to know the exact MRP that generated the reward sequence to uniquely to find this correct optimum. But the projected Bellman error and also TD error, projected in TD error would be unique for this, and are uniquely identifiable from the data distribution. And also in both cases, we have a corresponding W that minimizes the projected Bellman error or TD error. All right. So that is kind of, I do realize that this is kind of a bit complicated, and maybe I'm not doing the best job of communicating the ideas behind it. But the final conclusion we can get to from here, that all right, we can try to minimize the projected Bellman error in this case, and that would result in a unique optimal weight vector W. So the projected Bellman error is learnable, and we can learn a unique parameterization for our function approximations that minimizes it. And hopefully that at least makes some sense. So let's have a look at how can we derive the true gradient for projected Bellman error, and what are the trade-offs we have to do here to make it run. So again, the projected Bellman error is just this value expected delta sub W multiplied by this projection matrix, which depends on the feature vectors. So how do we represent our states, and the state distribution mu. And this matrix D here is a diagonal matrix with the weightings, the weights corresponding to the mu. So it represents our state distribution. And yeah, so here we just expand it. So we have here this mu2 norm of this value, then we expand it, then we can reorganize it, and so this would be just expanding the projection matrix. It can be found a couple of pages earlier in the book. Okay, and so basically by applying some rewriting using standard linear algebra, we can get to this form. And this form can, so we have this three components here, and you can see that, so this one and this one are the same, but here we have it transposed, and this one would be just the expectation, kind of expectation of squared x, right? So again, here we have some other derivations. So we can write this, take this component of the expression and write it as a sum over all states, mu times x times this error, and that would be again the same as this one here. So the expectation over states of the importance weighted error multiplied by the feature vector. And we can find a gradient of that quantity, and also we can find a gradient of that quantity transposed. We need it for this component of, so we took a gradient of this right here, and yeah, so now we kind of write down this gradient in terms of three expectations. And why do we need that? Because we want to sample from some, so we want to run a stochastic gradient descent. So we want to sample some values and use that sample approximation for the gradient. And so we have this three expectations here, and we have the same problems that we need to sample S sub t and S sub t plus 1 independently, but there is a way to to like work around it. We can, instead of sampling all three values here, we can compute this expectation explicitly and store it and sample only one value. And in this case, we have a choice what we want to sample and what we want to store. And it is most efficient to store this value. So this product of two expectations would be a vector of size d. So we want to have it not a quadratic in complexity, but a linear in memory. And that is the way to do it. We can store this value, and we can so this expectation depends on the distribution of the data, right? So we can update it iteratively. Each time we have a new sample, we just update this vector, and therefore we have a stored expectation of this quantity. And here is an update rule to compute this vector v iteratively. So it will be this one. We take we have some learning rate parameter, and then we just do this kind of update. And so this is similar to least squares problem, by the way. So they mentioned here that this is a least squares problem, right? We have a squared vector here, and we can update it. So we just introduce the important sampling ratio here, and yeah, so we need to minimize, we need to find v that minimizes this error, and yeah, so that would be it. Okay, and the second part, we still need to sample the remaining quantity and update our weight vector. So now we have two vectors. Both are, in case of, again, we are talking here about linear case, and in linear case, both vectors would be of size d, where d is the dimension of our feature vector. Right, and again, here we substitute this newly obtained v into the update using this gradient of projected Bellman error, and we get this update rule. Or alternatively, we can do a bit more math and get another update rule, which is claimed to be better. This last update rule will be what is known as the TD with gradient correction. So it's called TDC or GTD0. And the previous one is known as GTD2, I believe. So, and by running this algorithm, we have this convert. So now you can see that the weight vectors are not divergent in this case, but convergent to some values. But notice that, so again, our gradient descent, we are minimizing the projected Bellman error using gradient descent. And you can see that as the projected Bellman error is driven to 0, but the value error is still around 2. And that is not ideal, obviously. And why this happens? So when the projected Bellman error gets close to 0, the gradient gets close to 0 as well. So we have a very small gradients here. So basically the gradient vanishes, and the updates, although those should be going in the right directions, are very, very small. And here in the book, they claim that it should like converge to 0 eventually, but probably that will take some enormous amount of running time to converge. Okay. And again, we have this extra cost here. So we have we need twice the memory as compared to the algorithm we used before. And also we need to do more computations. But this algorithm is convergent, and the projected Bellman error is minimized. And yeah, I have this stuff implemented here. You can also play around with it if you'd like to, and you can see that when we use expected updates instead of sample updates, it converges like smoothly, but also it is convergent with sample updates nicely, and it converges in both cases when using GTD 0, or we can use, just out of curiosity, I was trying GTD 2 here, and I believe it has very similar results. So you can see that the plot is very similar, and we still have this problem that value error kind of converges very slowly in this case. Yeah. Also, I was trying to run it for longer. Let's say we can do, instead of 1,000 sweeps, we can do 100,000 sweeps. It will take quite some time, but if I remember it right, it did not improve much. You can see that, yeah, it's like virtually no improvement here. So they say it converges, and you can, if you look really closely, you can see that the values are not like this. These are not straight lines. These are still changing like really a tiny bit, but yeah, that's not what you would call a great convergence in this case. But again, remember that all these results are for that particular Bart's, I'm not sure how the surname is pronounced, counterexample, which is like specifically designed to be difficult for off-policy learning. All right. Okay, so that is TDC, and there are so again we have this two learning rates, and there are convergence proofs for this kind of algorithm, which are kind of So this is called asymmetrical dependence cascade, and there are some requirements to the learning rates here, so that we have a guaranteed convergence. So we should decrease beta value towards 0, and also the ratio of alpha to beta should also in limit go towards 0. And yeah, so this is a popular algorithm, and there are extensions of this algorithm applied to eligibility traces. That is the topic of the next chapter. And the eligibility traces is just an alternative. It can be thought of as an alternative formulation of the temporal difference learning, and which is more kind of computationally convenient. And there are these algorithms with proved convergence for eligibility traces case as well. Okay, so that is one possible solution for this problem, but again, you can see here that as we optimize the projected Bellman error, our value error might still remain far away from the optimum. And once projected Bellman error is close to 0, we are converging. So the updates are really tiny and we are converging very slowly. And another way to approach this problems is emphatic TD method. And it was briefly introduced in chapter 9, I believe. And let's have a look at what is that. So to use the emphatic algorithm, we introduce 2 new quantities. So one is interest and another is emphasis. And the emphasis is defined as given here. So it is our discount rate multiplied by the importance sampling ratio times the emphasis at the previous time step plus interest. And basically, what would it do if you think about it? So it will be it will depend on the how the trajectory, the observed trajectory, how relevant is it to the trajectory of interest to our target policy, right? So imagine we are taking actions that are the actions corresponding to our probable under our target policy, then the importance sampling ratio will be greater than 1, and the emphasis will increase. On the other hand, if we are if we have taken action that has 0 probability under target policy, we will have a 0 value for importance sampling ratio. Therefore, the value for the emphasis for the next update would be equal to the interest only in that case. And here you can see that we multiply our update by the emphasis. So we have the learning rate, emphasis, and importance sampling ratio, and we multiply the our error times the gradient by all these 3 quantities. And as you can imagine, this is very this is very high, this has a very high variance, the learning in this case, and if so it will work only in that cases when our behavioral policy is relevantly close to the policy of interest, to the target policy. So, for example, if we have something like epsilon greedy policy as behavioral policy, and we are learning the greedy policy, or we are trying to evaluate the greedy policy, then it probably should work better compared to, for example, using a random policy as behavioral policy. Because in that case, this value can grow quite high, and the update may diverge, and we will have a look at it in this example. And the intuition behind this method, you can see this explanation in terms of pseudo-termination. For example, having a decay rate of 0.9, you can think of it as a process equivalent. So it is equivalent to having a process that terminates with probability 0.1 at each time step. And in this way, the discounted formulation can be viewed as a pseudo-termination. So when using discounting, we kind of terminate at each transition with some probability, but instead of doing it stochastically, we do it kind of in expectation. And here you can see that we multiply the emphasis by gamma, and therefore the impact of the emphasis at previous time step eventually is shrinked by factor gamma. So, and there are some so we have this experimental results for this method, but as I mentioned in the book, this algorithm did not converge with sampling, so they used kind of expected values to produce these results. And you can see that in expectation, the value error eventually, so it fluctuates, but it eventually is driven towards zero. So that is great. Our true value error is driven towards zero. So we are learning the weights that actually are optimal for that problem. But here you can have a look. I have this implemented both in expectation, and I can see that results are matching those from the book. And here we have a case when we do sampling, and you can see that these results are kind of crazy. And you can see that the difference between runs is also very significant. And this would also work better if we would have a lower value for gamma. Here I change value from 0.99 as used in Bart's counterexample to just 0.9, and let's see what happens. You can see that there is still a lot of variance, but this time it is substantially lower, I guess. Yeah, and if before we haven't observed something that was looking like it converges, this time we even have some nice runs when we are seemingly converge towards some solution. And if you decrease it even further, you can get a stable convergence for the sampling case. But again, as you remember, we usually want this value to be high, and that depends on the problem we are facing. For some problems, we really want to the value of some state to be affected by the rewards observed many steps ahead, right? And in that cases, we want gamma to be high. All right, so that is two algorithms that are trying to solve this problem of divergence when using off-policy learning with function approximation and bootstrapping. And yeah, both have their issues, but I believe both are applied in practice, and yeah, have some nice proofs of convergence, but also have some weaknesses. And there is this final short paragraph, like section of the book on reducing variance. And as you might remember, we were using, for example, weighted importance sampling in the tabular case, and that helped a lot. But in this case, I believe there is no such nice way of reducing variance. But there are, yeah, they mention here weighted importance sampling, and again mentions that adapting this to function approximation is challenging, but there are some works on it, and yeah, if you want to learn about ways to reduce variance, I believe that is a topic of ongoing research, and maybe we can check out some papers on it if we face this problem further down. Okay, and to summarize it, the off-policy learning is a challenging problem, and still an open topic in current research. And we want to use Q-learning, for example, often, and Q-learning is an off-policy algorithm. Therefore, we are the researchers are really interested in finding efficient solutions to this issue of convergence of classic algorithms when applied to off-policy learning with function approximation and bootstrapping. So yeah, and we were introduced to these two methods here. And yeah, it would be really interesting to have a look at how this relates to some results that are published on some, common benchmark environments like Atari and other. So I believe their function approximation is definitely used there, and I think that off-policy learning is an important part of many like learning frameworks, and bootstrapping helps a lot when to speed up training. So it would be interesting to see how this challenge is overcome in the successful approaches. And I believe the DQN, so which would be deep or DQL, deep Q learning, is an popular algorithm, and it's often used as a baseline, and it is using function approximation, particularly neural networks for function approximation. Yeah, so that I believe we will encounter this more if we will proceed with reinforcement learning. All right, and I guess that's everything I had here. Yeah, I believe I showed this simpler two-state counterexample last time, and in this case the emphatic TD converges nicely while semi-gradient TD diverges. So that really depends on the problem, and for this very simple problem, emphatic TD does work when we use sampling. All right, so if you have any questions or comments, please jump in, and if not, I think Mayank will introduce us to some details of the Flatland challenge, which is an interesting problem that people are trying to solve, a real world problem that people are trying to solve using reinforcement learning. But the classic methods are still outperforming reinforcement learning in that area. So yeah, that is a really interesting challenge and topic of research.
Yeah, if you're talking, we can barely hear you.
Okay. Can you guys hear me now?
Yes.
I think so. My mic is a bit okay. I think this is the first notebook that you get when you sign in on the Flatlands environment. So let's get started with Flatlands, what it is, and as Otto alluded to, it's a very easy challenge based on the number of years it has been since this challenge was presented, but until now, the reinforcement learning methods haven't still been able to surpass the classical operational research methods and the hybrid methods that those teams have formed to solve this. So this is the challenge: how to efficiently manage the dense traffic on the complex railway networks. It's basically a vehicle rescheduling problem that they have tried to solve, and I will show you a basic reference as to how this thing works. As you guys can see, this is the environment, and we have 7 cases, 7 plus 1, 8 cases of the environment in which the vehicle or trains can move. So straight, simple switch, diamond crossing, single slip switch, and so on. So this is the 8 unique cell that help us to implement any real world railway network in the flatland environment. And the actions are these: nothing left, forward, right, and stop moving. By default, it's moving all the time. These are the observations that we get. Global is since we are using multi-agents. So for a global agent to view all the other agents or all the other routes and all the other paths with respect to everything is difficult because the amount of memory that it consumes per agent, it's large. So what we do is we implement a kind of a tree network at every stage of our agent behavior, of every step of our agent behavior. So in every episode, we have a kind of a tree network in which we can see the future observations or of a particular time step that they have tried to complete or which are currently visible from the perspective of a particular agent in its future. So tree is a kind of, as you guessed it, yeah, it's simply root and some nodes which are implemented as a kind of a data structure here. So yeah, we have the environment which we can go into the details of how they have implemented it. And then Then the other one is the local one, in which an agent only shows a local intersection of a particular railway network that it sees. So yeah, that's what it is here. Then rewards. As you can see here, we have a -1 on the number of time steps train can run on a particular track, and when it arrives, it gets a 0 reward, the latest arrival. And for a train that is never that has not reached its target yet, it is the current delay time, that is that the clock starts when the train starts from its source destination. So the train never departed, and this is considered cancelled. There are other factors too, as we will see. These two factors, how they affect our environment and the flow of our total coming up next is the rail in environment. Okay, let me try to use it. Use the rail environment here. So as you can see, this is a simple flatlands.environments package in which we have all the major classes there, classes here. So we are constructing a sparse rail we are simply forming a sparse rail generator here with a maximum number of cities too, and the properties of the environment will be the width will be 24, height will be 24, the number of agents is 1, the number of rails generated will be the number of cities, that is 2, and the sparse line generator, that's the default that we are taking, and the OBS builder object, it's global OBS for the rail environment. Here, as I have alluded to, we had global local entry, so we are taking the global here, global observations. In this case, since we are only running the single agent here, so we are visualizing the environment. As you can see here, the render in environment method, it's a simple tool that gets a PIL image from that array of the render tool that we have. So a flatlands neutral render tools package has a render tool class that uses this to display us tool. So every time if I run it, a new environment will be a new random environment will be formed. So which having a particular number of how do you say it? The number of railway lines, the crossings, the number of stations, and all, as we have defined it here. So this is a custom gym environment type interface that we are using. So that's the same environment, and these are the observations that I've alluded to earlier: global, local, and a tree. For the challenge part, we will be using tree, but currently we are using the global map. And here you can see the number of transition maps, the agent positions, and the agent targets. So these are in the agent handle, which are being presented by the random in environment. Since we have so these three things: the transition maps, the agent positions, and the agent targets help us to make our way through that particular environment that we had. So we will see how we can use them in the next. So here we talk about the agent. So agent, we are using the RLLibs multi-agent in environment class 2, but here the environment is run by using steps, as I've alluded to, by using the number of time steps that a particular episode has. And until the episode terminates, we will be using it to update our policy, and until this done render all is doubly pushed through. So until this episode terminates. So this is the random controller that we try to build, and it's simply trying to update the action, taking the observations. That's the agent handle under observation, and the agent handle is being updated depending upon the next state action, next random action it has taken. So as we had 4 or 5 actions, so depending upon that, this is only selecting a random action from our whole list. So on a cross section, our agent can go left or right, and depending upon the value that it got from that particular time step. This is defines the environment.get handle, like get agent handles. This is totally like the Open API's OpenAI's gym. It's constructed to feel like that. So this is a single action per agent. In the random environment.step will give us next observation, all rewards, dones, and info. So these are the 4 objects that we get. Yeah, rewards, done, the miscellaneous info that we get for a particular action. So as you can see, the agent 0 will perform action 4, that is stop, at Rewards for the each action is 0, 0, false. The number of duns for each agent, and the miscellaneous info, that is the action required, the state, and yeah, this information that is required for our smooth handling of our trains, our agents. Here you can see in the run episode method, what they have done is a simple random controller and observations, and they have given a loop as to iterate our controller's observations and take a step depending upon the agent agents what how do I say it, how do an agent particularly handles that particular environment, and it's the same here. The score is being added here, so the score is totally dependent upon the time step here. So yeah, that will be added, and if the episode didn't finish after 50 time steps, then yeah. Let me try to show a current running version of it. So you can see here, this is the time step 1. Time step 1, our agent appears here. Currently, I think so it's at a stop. So yeah, it's currently moving one step at a time, and its final location is here. If it reaches here, then our environment is considered stopped, and it should reach here in under 50 time steps. So if it continues to move in a straight line after it has taken this turn, it should reach here. But since our policies our policy is random, at each time step, our agent can take any left, right, or stop state. So yeah, I'm not sure. It has taken the right here. So you can see. So it won't be reaching. It has taken a left here. It should take a straight. Yeah. It has taken a left here. Then again. So this is a simple environment that you can construct and play around with it. That's a simple one agent environment, but in so all done. The time steps 31. Total score was -57. So it has crossed this particular line. So yeah, it's currently showing solved. You might try another way to do it. Different simulation. So this is it. This is the basic form of what they are trying to solve. So consider here multiple agents, multiple trains. These agents that are there in which they are trying to reach multiple destinations. They have given a gift there. This was a sequential agent. Okay. I'm unable to find it, I guess. So yeah, this is a simple operations research in environment that I've shown you earlier. This is a reinforcement learning based agent, as you can see here. This is a kind of a sequential. Uh, here we have 4 or 5 trains that are appearing at the beginning of the episode, and they have to reach their destinations. And this is done using DQN. And so we can use DQN to the next. This, as I've alluded to, this was by using a single agent, but we will be using multiple agents next time. So yeah, that's the challenge here, to solve it under a particular time in and the particular score. I think so they are maintaining the scores here. Yes, this is the evaluation metrics. This is the time limits, and there's a leaderboard too. Evaluation matrices. So the leaderboard, in which this is a competition that's currently ongoing. The folks have tried. They have implemented their code and using the RL, and there are various benchmarks on which your multi-agent is evaluated, starting from the simplest to, and it scales up. For example, it has the first has 2 stations and 2 agents. The next has 4 and so on. 6, then 10, and then 12. It scales up. So how many challenges are you able to cross depending upon the number of the number of I think so your submissions, depending upon the map and the number of submissions that your particular code was able to cross in a particular time. So that's the currently how do I say it, the full of this particular challenge, and you can also see the stats and the code of the particular agent that had reached. They will be available after the based on your access permissions. So you will have to request this wave team or to request permission to see their code, and they might provide access if they feel, but there is some goodies to be won. So I think so it will be available after the competition ends. But yeah, it's a great way to implement some of our theoretical concepts that we have learned through this whole book. Yeah, so I was thinking, let's do this. Currently, I have this at my table. Thanks, guys. So I think so we can end.
Yeah, thank you, Mayank, for bringing this competition up. And yeah, it would be really interesting. I think maybe next week we can check out some best solutions presented in that talk you posted a link to. Right, so I believe they from the last year there were like a presentation of a best solution using some classic planning methods, right, and two reinforcement learning based solutions, and also they have, I believe the organizers presented some baselines there. I haven't watched the video yet, but I guess it would be interesting to discuss what people used there and.
Yes, yes.
Yeah, and also it's kind of still a bit like curious that reinforcement learning is showing some nice results in some really complicated environments like Dota, for example, but here it still performs relatively bad compared to other like more exact solutions, right? But probably I wonder if that is mostly depend on the time constraints they have, or are there some limitations of current RL approaches? Yeah, it would be interesting to figure that out. Okay. I think see you next week then, everyone.
Thanks, everyone.
Okay, thanks, Arlo. Thanks, Mike. I'll take a look at the competition. Get back to you next week.
Right.
Cheers.
Bye.
Cheers. See you next week. Bye.